Alrighty, well, we'll go ahead and get started. Isaac Smith is going to be presenting today. So Isaac, go ahead and take it away.
Yeah, thanks. This is something I've been thinking about for actually quite a few years, and I'm finally getting to the manuscript. I've got a couple of pages written, and I'm doing the background research. Turns out literature review is something I enjoy, oddly enough. And so I'm diving deep into the really early Mariner stuff to figure out what was exactly said. Because I want to follow the line of thought on this, going back to Mariner 6. Yeah. In the no-flow scenario for the polar layer deposits on Mars, I'm suggesting here that the PLDs don't flow, or if there's any flow, it's so small that we can't actually measure it, and there's no observational evidence in support of it, which means probably millimeters per 1,000 years or something, really, really slow. And that's compared to glaciers on Earth, where we see flow that could be on the order of meters or hundreds of meters per year, not millimeters per millennia. I want to show several things. On the left here, we have an actual glacier that's deflated now, but you can see the moraines that are left over. Ice flows on Mars, or has flowed, at least in the past. There's a North Polar layer deposit. It's kind of a perspective view, and you can get a nice idea of what's going on. The spirals, the giant canyon, got huge cliffs on the sides. None of those things would exist if it were flowing fast. And then some cookies here because I'm alluding to a reveal at the end. All right, so like I said, glaciers are abundant. We have lots of flowing ice. We see it in lobate debris aprons. This is a mountain or a massif, and off of that's flowing these glaciers, and you can actually see some of the flow lines. Here it's even more apparent in the lineated valley fill. Between mesas, you can see ice has flowed downhill like that. And then there's a concentric crater fill. And this is a place where you have ice flowing down into the crater, creating these circular lines, but it's all ice. And this is all generally considered viscous flow features, VFF. Yeah, and so there's abundant evidence. For instance, in Deuteronalis mensa, we see a lot of lineated valley fill and these lobate debris aprons all over the place. Here's an example of one. We actually have ice that flowed on top of other ice. So you have multiple stages here of ice burial. In Eastern Hellas, this is one of the first ones that we used radar to discover. They were known about for years, but we hadn't been able to identify what the material was. And so we didn't know if there's any ice left, if they were rock glaciers, if they were actual glaciers covered with debris. And so we call this lobate debris apron, but it's really a debris covered glacier. And this is the one that's being shown here. And there's quite a few others. And these things can be 700 meters thick. I think some on Mars get to be like a kilometer thick. Here's one from a group at PSI. Daniel Berman led it in Argyre Basin, southeastern part of Mars. And you can actually see the tongue of one of these glaciers. And there's plenty of other ones that are smaller. These in the order of a few hundred meters. So lots of evidence of at least past flowing ice. We don't see any currently flowing ice right now. We're keeping our eyes open for that. So this is from Joe Levy's 2014 paper of all the different types of viscous flow features. They stopped mostly, and you can see the straight line there. It's not a natural line. That's one where they stopped looking primarily. That's around 50 degrees, but there's tons of these. There's probably thousands of them, and more that Joe didn't map. And mostly in the mid-latitudes. And here's one from that same Dan Berman paper where you see a bunch in the south. There's actually more here than Joe mapped. This is in 2021, where Neridium Montes is part of Argyre. There's a bunch of them in here. So what about the poles, right? Mid-latitudes? Well, do the polar layer deposits flow? That's the question. And it's been on our minds for a long time. We've known there's been polar ice since Galileo and Herschel. So we're talking many centuries of knowledge that there's ice at the poles, although seasonally it comes and goes. So they weren't sure about what was there. And then I put this some evidence but disproven. You can interpret things one way, and then later on you make a prediction, and then you get new data, and it just totally negates your prediction. There's a few cases of this where people suggest there's flow, but then the next observation says absolutely not. Let's see. Okay, so this is my shorthand for what flow should look like. Anyone who's baked cookies or done anything else with maple syrup, you see it kind of just flows outward when you put it on a plate. until it reaches some equilibrium. And that equilibrium has to do with if you have accumulation in one spot and ablation in another. But in general, you should kind of expect a dome shape. And that's exactly what John Nye said. John Nye is a famous glaciologist going back to the 50s. He took a look at this in 2000 and said, if the polar caps are flowing, the PLD flowing, then you should have this kind of dome shape. And the dome shape depends on several things. One of them is the stress exponent. So this N is the exponent. You take the stress, which is rho GH in most cases, and you put that to a power, and that can be 1.8 to get this kind of shape. If you have 0, then you end up with a much taller dome. If you have a higher number, you get a much lower dome, but it's still overall a dome shape. So he's saying essentially the PLDs flow, they should have a dome shape. And if they differ from that, then other forces are acting on the PLDs at some rate that either competes with, is less than, or much greater than the flowing. So this is the year 2000. That happens to be the same year where we get the first North Polar actual topography data from MOLA. There had been some, not radial occultation, but like occultation studies to get the kind of topography, but we didn't really even know how thick it was until MOLA came around. And so this is Kate Fishbaum and Jim Head, and they get kind of a dome shape. You can kind of see that, but it's immediately apparent there are other things going on. There's the spiral troughs, which are abundant, and then there's Chasm Boreal, which you can see right here. It's a deep canyon about the size of the Grand Canyon in depth and width and length. And so this is the 3D perspective view that they made. Pretty impressive for the year 2000. And then this is, these are topographic profiles going along the 90 line. And then this is, from a different perspective. So I guess the lines are a little different. But yeah, 90 west to 270, 180 to 360. So it's dropping up like a plus sign. And it roughly looks like a dome, but it is not dome shaped because it has all of these cuts in it. And so it turns out the spiral troughs have been a sticking point since the very beginning. If you go back to 1971, that's an issue. So this is a Belcher, Vaverka, and Carl Sagan paper from 1971 looking at Mariner 6 and 7 data. So these are flybys. And they just happened to get a couple images of the South Pole. And they saw these ridges here. They thought, oh, ridges could be moraines. We know that there's ice there, and we know that when ice moves, it leaves moraines, and so perhaps that. And they also suggest, although they say note the wraparound lobe suggesting flow around a topographic high. I don't even know what they mean by that. They don't have an arrow there, so it doesn't help. And these guys are all gone now. Turns out that these are terraces related to the spiral troughs of the North Pole, and they have pretty steep slopes, and so they're not actually moraines. And it wasn't even that long. So in the same year, 1971, Sharp, Murray, Layton, and Soderblom, 4 big names in early Mars science, and still big names, and cuts, argue that these were edges of platy layers of remnant ice, basically terraces, and suggested that wind is a possible erosive agent. So already at the very beginning, some people say flow, and some people say no, it's probably wind. So this is the dichotomy that we've had forever. Carl Sagan, and I love citing Carl Sagan's papers because it's just fun to do. In 1973, I don't have the year, but this is 73. He said liquid carbon dioxide at the bottom of the polar deposits, so the ice could be thick enough that if there's CO2 at the bottom, you could melt it. That would cause, liquefies as laterally transported by the weight of the overlying solid layers that do not float in liquid. So basically, you have basal sliding, which is a type of flow, or it fits in the glacier category. So he's saying that in 73. Quickly ruled as unlikely because the PLDs were thought to be too thin and too cold for deformation. Remember, we didn't have good topography then. So Sharp concluded they probably do not and have not in the past acted like large terrestrial glacier ice sheets in terms of scour and deposition. So no moraines, you're not moving anything around. So this was in 74. Concurrent work found that CO2 ice was unlikely constituent. So this is Ingersoll 74 and Kiefer 76. And so it's probably not CO2, although that keeps coming up. That was even around in the year 2001. John Nye published a paper thinking about that. In 86, there was a paper by this guy, Ruud Weiermars, suggesting that there was glacial flow. And he looked at this, which is upside down from what we're normally used to seeing. I'm using his figures as they were. I kind of like it because it's an upside down idea too. He suggested that the Coriolis force would create the spirals, and the spirals would form through glacial surges. And here's an image that has a topographic high near the North Pole, and the ice is moving outward in surges that would create fracturing, and the fracturing was the spiral troughs, according to his idea. Regions of Mars are fractures which form perpendicular to gravitationally driven flow lines deflected by Coriolis forces. And he shows some examples, but they're not usually spiraling. They're usually kind of arcuate shaped when you have terrestrial valley glaciers. These fractures are crevasses that form perpendicular to the direction of flow have been reported from terrestrial glaciers. There you go. And at the end, he suggested that you need to flow 0.2 meters per second. That is fast. We're not talking now meters per year. We're talking about meters per minute. And so you'd have to have something like a major basal sliding event or something to create this. And we already knew that wasn't true. So the stratigraphy predicted by this, 86, was not, we already knew that didn't exist. In 82, Alan Howard, James Cutts, and Carl Blasius had already done all the stratigraphic analysis they needed to say, no flow at all. These things are 100% wind. So here you have exposed layers and you have what they call banded terrain. And there's all over the cap. And what you end up with is these different scenarios. They have several of them in this paper. It's an 82 paper, I should have put that, where you have an unconformity, where you have new material draped over exposed older material. And we totally see this with the radar. I had a 2016 paper about this and how that looks like an ice age. They looked at other troughs and saw similar unconformities, or they saw a trough migration where the trough used to be here and it's migrated towards the pole uphill, when you have layers being thinned here due to wind erosion, of course, and redeposited that material here. And these guys just nailed it. It's just absolutely perfect. And as early as 82 using Viking data. So this was an awesome early study that just showed if you don't have any flow, the layers are flat, except for where there's been erosion and unconformities. And they said deposition on the polar flats, but possibly also by eroding deepening of the troughs. So talking about how the troughs form themselves. Most also involve an increase in volume of the polar deposits through time. This means growing the cap, because in order to create these things, you have to grow the cap. If troughs do migrate poleward through time due to erosion on the equator-facing slopes and deposition on the pole-facing slopes, they may originate to the polar edge and then evolve and form in relative rates of erosion and deposition. So they're moving inward, they're migrating basically. This was dead on. Yeah, so Alan Howard is now at PSI, and I'm glad because I've worked with him in the past. He's on a paper that I published in 2013 looking at the radar stratigraphy of this. Here's the uninterpreted and then the interpreted or annotated version. And what we see is almost exactly perfectly what Alan Howard said. In the bottom, we have these mostly flat layers. And then up top, we see the troughs when they interact, create a pattern of erosion and deposition that almost perfectly matches what he showed. Here we have thin on the high side and then thickened layers on the low side. Here's a cartoon that shows it nicely. You get the migration path. High side is thicker layers or thinner layers. Low side is thicker layers. This is what Alan Howard showed. He says on the high side, which is topographically higher, you have thin layers. On the low side, you have thick layers. And you get a migration towards the pole in time. It was perfect. There's, yeah. To me, this is like the whole story. And Alan Howard got it in 82. Oh yeah, so these are some slides that I've been working on. Didn't quite finish. So this is what Alan Howard saw. This is the idea that the spiral troughs don't migrate. So this is something that Alexis Rodriguez, who's also at PSI, published about last year and multiple times. And we just don't see evidence for this at the North Pole. There's like one place you can find evidence, and he uses that. The South Pole is a different story, though. The North looks like this, the stratigraphy. The South Pole looks more like this, where you have layers that have been cut out. And then more recently, there's deposition on the low side. And so they're starting to migrate, but they didn't form that way. Or the North, they just formed by migration. And this is from Alexis's paper. He's saying that they're just cut in place. And that's true for most of the South Polar ones, but it's only true for maybe one of the North Polar ones. So I have a bone to pick. I'll leave it here at that. Okay, so why am I talking about the troughs? Well, it turns out that the trough stratigraphy is a very good clue about if the North Polar layer deposits are migrating or not. So these are predictions by David Fisher, who's a Canadian glaciologist. He's saying that if flow occurred during the evolution of spiral troughs, the subsurface stratigraphy would respond. So you have a depression. So here's your trough. And in that depression, you'd have less mass than you would over in these other places. And so due to, you think about viscous relaxation or flow, you'd flow towards the place with less mass, which basically ends up pushing the material up. So this is 93 and this is a 2000 paper. This is the prediction for stratigraphy if the cap's flowing. And these are annotated from his earlier papers. This is kind of similar stuff by David Fisher. He's predicting upward velocities here, pretty strong upward velocities. And so that's just matching that. Christine Vidberg did the same thing. She actually had the topography for the first time. So she was using topography from MOLEM in 03 and published this and said, look, if you have flowing ice cap, then the vertical velocity underneath the troughs is very high compared to everywhere else. And so what you're going to have is stratigraphy that matches what David Fisher said in 2000. She said, assuming that the permanent North Polar cap of Mars consists of flowing water ice flow velocities are enhanced at scarps and troughs to centimeters per year. Ice flow smooths out the troughs, which we don't see, and then troughs affect the flow to the bottom of the cap. Beneath the trough, ice is dragged upward, just like that stratigraphy. Well, it turns out we just don't see this at all. So I've done a very in-depth survey. I've done multiple in-depth surveys of the cap, and I've looked at from all different directions. These are using radar to get the stratigraphy. And in all the surveys, there's absolutely no evidence supporting this idea that the ice is moving upward beneath the trough. In fact, we see something quite different. We see, well, exactly what Alan Howard predicted, or actually saw because he observed it. So instead of the troughs having stratigraphy that moves up, we actually see this thin side and the thick side. High is where erosion is happening, low is where deposition is happening. And we see this down to about 1 kilometer into the cap. So this process, whatever it is, and it turns out it's wind, erosion, and deposition causing migration, has been going on for about half the age of the cap. We don't see any evidence of upwelling beneath the troughs. The layers tend to be pretty continuous there, especially in the lower section. So I think that really defeats the Fisher and Vidberg model. So in 2008, Dale Weinbrenner came in. He's a glaciologist on Earth also. He uses topography data. Here's a hillshade. And he created what we call flow lines, starting from a topographic high in Geminalingula. And he smoothed it. So this is draped on top of actual data, but he smoothed the data to get flow lines. And you can see that they would tend to flow kind of like they do. And you might get a topographic profile similar to what you see here, except he had to take out the spiral troughs to do that. This made very specific predictions that the spiral troughs all formed after flow was completed. But there's some problems with this. First of all, I already said the troughs have been around for about half the age of the cap. So we're talking of millions of years. Weinbrenner's prediction is this, that you have pretty smooth layers that thicken on the outside of the cap. And later on, the spiral troughs are cut in. But we just don't see any of this at all. So Weinbrenner's stratigraphic prediction is negated perfectly by the spiral troughs. It's incompatible. Later on, Nana Carlson came in and took Dale Weinbrenner's flow lines, topography, prediction, and ran the models. And she smoothed it and said, this is what it should look like. And so this looks, if you look closely, this is almost exactly what Dale Weinbrenner said. You should have thickening towards the edges, and then the troughs will be cut in later. And then she laid that on top of the actual data. She said, there's nothing that doesn't look like that at all. His prediction of stratigraphy and shape, the shape kind of matches if you take away the troughs, but the troughs actually just erase, they don't allow it. She said, if troughs represent ablation zones, then one would expect the isochrones to bend upward toward the surface there. She cites Fisher 2000. However, this is not the case. In other words, we find no evidence from the internal reflectors that the mass balance of Geminalingula has been dominated by accumulation, or which is accumulation in one place and ablation in another. We just don't see evidence for flow. Therefore, the observed reflectors do not match the upward bending morphology expected beneath the troughs coexisting with flow. There's no evidence of flow, according to this 2014 paper, or 2011 paper by Nana Carlson. All right, what about other predictions? So Mike Sori and a few other people that are formerly in Arizona said, look, we should have flow. And if we should have flow, then we can test it at some places that might be flowing fastest. And so they picked some of these really steep scarps that are on the order of 70 degrees, some of them are even closer to 90 degrees. And why is this a perfect place to test? Because if you have a steep scarp, then you're most likely to have flow outward right there. Ice or flowing material loves a steep slope. The steeper the slope, the better. Remember that exponent to the n. Well, if you have a steep slope, you get a lot greater stresses. And so here are your stresses, and they're predicting velocities on the order of meters per year, so 124 centimeters per year as the vertical velocity. And the x and y velocities are also pretty close to a meter. If you have the steep slope, you should be seeing it move outward by a meter per year. They said, well, if it's not moving, then it's probably because of erosion. So you're eroding fast enough to erase any of that record. Well, as soon as you can predict something, you can falsify it. So this group, Farnaro, Venner, Halber, and Oberst, these are German kind of permafrost guys. They looked at the erosion rate of the polar scarps, and there's tons of evidence of these block falls or avalanches, if you will. Tons of it. We can take a picture and be guaranteed to get several at a time in the northern early spring. So they got an idea of the mass wasting rate or the erosion rate. They said the erosion rate cannot counteract published estimates of viscous flow features. This was in direct response to the story paper that said we should have a meter outward per year. And they said, no, you might get 0.2 millimeters per kiloyear. So we're talking multiple orders of magnitude too slow of erosion to offset what would be flowing there. And since we don't see flow, and the only thing that could offset it is too slow, then you don't have flow. We're talking 3, almost 4 orders of magnitude difference. So again, prediction falsified. All right, I'll set it up. This is an ongoing debate. We're talking 50 years plus of like flow, no flow, flow, no flow. But why? Why isn't it flowing? Is it just because they're colder? And some scientists have said that, right? There's the flow laws change with temperature. So colder ice should flow more slowly, potentially dropping the strain rate, which is the flow, well below that for other glaciers on Mars, potentially. But even if this were true for the NPLD, which is only a few million years old, the SPLD is at least 10 times older, maybe much more. It's experienced many warm periods that could have experienced flow, that could have been warm enough to give flow. And no evidence exists at either pole. So no evidence that hasn't been falsified at either pole exists for flow. And just to hit home on the point, Lascar in 2002 published this paper looking back about 10 million years and said that the obliquity centricity would have given us a much higher insolation rate. So you'd have had twice as much heat at the North Pole and the South Pole a few million years ago. And so this would have increased the likelihood, increased the surface temperature, and then the depth temperature. So you would have had more chances of flow. And this is true for the South Pole. If you go back maybe tens, like to 50 million years, you had much higher obliquities. And sorry for this horrible plot that I just pulled it out of that paper. This is now their 2004 paper. Much warmer temperatures at the poles. And so it's probably not, because if you've been around 50 million years and you've been really hot for 10 or 20 of those million years, you should have been flowing. So we don't see that. David Goldsby teamed up with Pathari. They had a pretty good idea. They said, how much non-ice material would it take to inhibit flow? And gosh, I'm going really slow, aren't I? Okay, they said there's a critical fraction, about 6%, below which samples behave like pure ice, and above which they slow down. the impurities tend to hinder things. And we know that the North Polar lake deposits is about 5%, so maybe it's 6%, and it inhibits flow. But that doesn't make sense because you have to have it all concentrated. And the vast majority, 95% of the North Pole is nearly pure ice, with only 5% having really high concentrations of dust. So here's my hypothesis. I'm going to get there and run out of time at the same time. What if it's the L in the polar layer deposits, the layers themselves? The layers act as boundaries through which ice does not flow, like a s'more. So you have the flowy layers that are ice, but then they're surrounded by the layers that are more brittle or resistant to flow. And if you have this, you can stack it up, and I have somewhere a stack of marshmallows. You can really, really inhibit the flow. So this is what a normal ice sheet looks like. This is the John Nye version. This is our 50-year-old assumption, is that you can have all these layers here, and it's going to flow just like a normal dome, minus the spiral troughs, which negate all this stuff anyway. My proposal is that each individual layer might be flowing, but we're talking about millimeters per millennia rather than meters per year or meters per kiloyear. Each one acts as its own compartmentalized flow, but the stresses on each layer are small enough that it pushes very little outward. So we don't see this, and then here's what I'm saying. So you have stacked thin layer flow model. From the bottom, the stresses are pretty balanced, and what you need is deviatoric stresses, so the change in stress laterally. So if you move from here to here, the stresses are very minimally different. So really only the margins can move. And this is true for each subsequent layer. And then there's these hard layers that impede the flow. They're basically the cookie part of the s'more. And here's your stacked s'more. So you have a little bit of flow, but not much. This has been borne out actually in the literature. So there's a couple papers by Key and G in 2018 and 2000 where they looked at stacked, and this looks like Oreos, I know, but these are different types of aluminum oxides, I think. And if you have oxides of different, or these materials of different rheologies, so different flow rates, and you push on them, some layers are going to flow more than others, obviously, and so you end up with this Oreo-looking thing, and it severely hinders. The bulk flow strength of layered composites increases with decreasing thickness, so the thickness matters, and then thin layered rocks compressed normal to the layering are rheologically stronger than homogeneous isotropic mixtures under the stone deformation condition. So this is basically going back to here and saying if you have it evenly distributed, it's going to flow much more rapidly than if you have stratified. Okay. Oh, and then, yeah, there it is, going back to that. All right, here's my punchline. I made some cookies. This is 4 pounds of cookie dough. I put them in 2 bowls. One bowl has the cookie dough, just the cookie dough. And the other one, I put some stratification in. Here's some paper, parchment paper I put between multiple layers. And in the end, they look identical from this side, and then I flip it over to make a dome, and they look kind of identical here, but they're not identical. One, and you'll figure out which one real quick, is just cookie dough, and the other one has stratification, and you can even see it. So this is the video, taking about once a minute, and sure, the bottom here is oozing, but remember, basal sliding is an issue. But look at this cookie on the left. It's really made that dome shape that's expected. And here we've had almost no deviation except at the very bottom. And that's because, of course, like I said, you can see how much oil comes out of these cookies. You have basal sliding. This is the same mass, the same material. Obviously, it's heterogeneous because it's a chocolate chip cookie, but it looks quite different here. Here's the final result. And the right side is stronger because it's stratified. So here's my conclusion. Evidence of polar flow is lacking, or basically disproven, even though modeling suggests that the PLD should flow on measurable timescales. So the hypothesis is that stacked thin layer flow explains the missing observations. And here is the cookie. I eventually heated it up and it did finish cooking. Here we have the glass of milk. And that's it. So I'm sorry I went over. Thank you. Did anybody stick around to see the whole thing?
Yeah, there's still a bunch of people on. If anybody
Awesome.
has any questions, feel
I
free
do.
to ask.
All right, go ahead.
Hey, what a beautiful and tasty talk. I love it. The your hard layers would
Yeah.
conceivably, if I understand your hypothesis, would conceivably nullify shear stresses across them, but they wouldn't nullify normal stresses. And what drives the flow outwards is the transmission of normal stress from the top of the stack to the bottom of the stack.
Mm-hmm.
Now, I'm wondering, I didn't do this calculation, I was trying to keep up with you, but I'm wondering if indeed it is true that if you nullify just the shear stresses, but keep the normal stresses on, that you prevent the thin layers from squeezing out at the bottom, or progressively.
So that's the hypothesis, right? And it's been borne out in the experiments. So they've done these experiments, and they've shown that because these are confined, so that you don't have so much shear, and it just bulges at the edges a little bit.
Yeah, but I'm not sure if it's the same scaling, because there you have gravity. I mean, these experiments, you just apply a stress from the top to the bottom, right? I'm guessing. And in reality, you have essentially, I'm not sure it's the same thing. Maybe it is. I need to think about it more. Because what you have is a gradient in normal stress that results from gravity, right? So the bottom layers are feeling the weight of all the layers, so they squeeze out more. And the top layers, less weight, so they squeeze out less. Whereas in the experiment, the normal stress is equal throughout the stack.
Okay, I agree with that. I do want to point out, though, that in these experiments, you tend to have a lot of outward motion. So in this D panel, they used just a single material, and they did the same amount of stress, and I think we're talking megapascals, and it bulges outward. And so
yeah, of course it does, because the stress is equal throughout the stack. Yeah,
and that's true also for B. The stress is equal throughout the stack, but some layers are more resistant to flow, and some are more readily flowable. And so, yeah, I'm working with a grad student right now. We published a paper in this year about CO2 glaciers on the South Pole. Now what we're doing is we're building a stratified, and this is a really hard, he's been working on it for like 15 months now, building a stratified 3D model to see how much it would inhibit the flow rates. And so I'm trying to get out this paper as my hypothesis, and we're going to immediately test it once that code is ready. So that's one way to do it. But
right thing to do. Yeah. Well, anyway, what a lovely idea. Thank you.
Thanks.
Alan Howard to make a comment.
Hey, Alan, please.
So it seems to me to have an effect, the more resistant layers have to be resistant to tensile fracturing. Because otherwise I can imagine that you just sort of break it into lots of little crumbs that wouldn't offer much resistance to lateral flow.
That's a good point. I think what we need to consider, and so this goes back to Oded's question also. If you have this motion, yeah, you can break the crumbs, but remember the slopes here are extremely low. So we got 1,000 kilometer diameter ice cap, and the steepest slopes, except at these cliffs, we tend to be in the 1 to 3 degree slope range, and so even over tens of kilometers, the stress is actually not that high. The differential stress between these two locations, it's enough that if you were flowing, you would see this upward motion right here. But we're talking still tens of kilometers. On a much smaller scale, the stresses, the deviatoric stresses, are really low.
Actually, can I jump in?
Please, yeah.
So I want to actually take your side and say, I think even if it breaks into crumbs, then the enhanced friction on that plane would still prevent shear stresses from being transmitted through, and it would still resist flow, even if, as Alan said, it would be broken into crumbs. It doesn't have to be a coherent layer to avoid transmitting shear stress. And my analogy, and I love this because it fits so perfectly with your talk, is I made a birthday cake, an ice cream cake for my daughter's birthday recently. And the recipe called for breaking up Oreos and putting it between the chocolate cake and the ice cream. And I didn't quite understand why, whether it just tastes better. But then I thought, hey, maybe they want to avoid the ice cream sliding off of the chocolate cake. So they had me break up Oreos and put them there. So I swear to God, this is a true story. So this is the reason.
I think so, dude. I've actually thought about redoing this instead of using parchment paper, which has a very strong tensile strength compared to cookie dough. I thought about doing it with crumbs, and just haven't got around to it. I need a few hours of like concentrated time at home, and I don't get that these days. But yeah, thanks for that, because it might be worth doing my own thing.
But Alan, what do you think? Do you think that broken material could still act as a frictional enhancer?
I don't know. The experiment rules, so we'll see what happens.
Mm-hmm. Megan posted something that says the broken up layer isn't transmitting the stress across large lateral distances. So yeah, you have the forces don't act over such a long distance. But I think that would require like a really solid, like a block of wood or something to transmit it. So if you break it up, yeah, when you think about like a bowl full of sand or something, you can push over here and it doesn't move anything on the other side. I think Megan's saying something like that.
Yes, correct.
You can compensate really locally if you have crumbs.
One way to perhaps test it would be to make your intervening layers just something like sand, because that would not have any resistance to extensional stresses except through the grains themselves. So if it was something like sand, it could actually, without cohesion, it could actually get thinner, perhaps have the same effect.
Yeah. Well, okay. I want to take it back to the Del Weinbrenner stuff, because he made a prediction what the stratigraphy would look like. And this is assuming no troughs, right? So where do I go to find that? Del Weinbrenner stuff is here. Yeah. So this is my version of his, and it should be thickening. But remember, if you're only thickening, if your layers are meter thick and you have a 10%, it's really going to be very small things, hard to measure things at these edges. Instead of having like here, he's drawn it kind of like hundreds of meters of thickening at this ablation zone. So I think everything just scales down a bunch, and that's the point of this slide, or really this slide. Everything really scales down when you have stratified flow. Some people have made the comment that this is not the internal stratigraphy. The internal stratigraphy is one that has unconformities in it. And so how do you transfer this across an unconformity? I don't think you have to. I think, we're talking about tens of kilometers. So the stress between here and here, even across an unconformity, really it doesn't change much. And so I think that if you were trying to negate it that way, I think it's a beside the point kind of argument. So that's one that I haven't answered fully yet, but I'm working on it. So this is my concept. I should have asked for 45 minutes on that.
Can I ask a question?
Of course, yeah, please do.
So we wouldn't expect to see any signs of this inhibited flow at the conformities. Like, I mean, the boundaries in these radiograms are drawn pretty linearly, but like, could we test it by, I don't know, a higher resolution data set looking at the actual, like the shape, like the path of the unconformity?
Well, okay, so I'll take that and I'll answer it slightly differently. There's something called boudinage, where you have a thin layer that kind of like extrudes. They call this extrusive flow. And boudinage happens on Earth. And there's one paper talking about one small spot on the South Pole where they had boudinage. I bet I can bring it up. And so, yeah, this is for rocks, where you can kind of pinch layers individually. And so there's but like 3 small examples across the entire South Pole layer deposits that suggested that boudinage might be available. So I think, Megan, what you're asking is, if you're looking at these layers, could you see some changes?
Yeah,
We don't see it, and I don't think the higher resolution is going to help, because if you do, oh my goodness, I don't have any backup slides, so I didn't make any. I'm sure I could find some. If you really zoom in on these layers, we just don't see that much deviation in them. And so, and I am not the first to say that. This is something we've been looking at since mock data, of just like how coherent these layers are across hundreds of kilometers.
yeah, that makes sense. Okay.
I'd love to, Alan and Oded and Megan, I really appreciate your comments. I'd love to continue this, because I'm writing this paper up, and I want to be able to address all the comments ahead of time, honestly. So this is why I'm showing it here, because I wanted to get a first round of thoughts. And yeah, I appreciate you tuning in.
Yeah, very cool. Thank you.
Awesome. Well, if there's no other questions, thank you, Isaac, for the presentation.
Yeah, you're welcome, and thanks everybody for coming.
Thanks, Isaac.
Sharing.